Fact or fiction? Earth once made its own nuclear reactors. Fact. But the stronger story is not just that uranium reacted in the ground. It is how scientists realized something impossible looking had already happened. The trail begins in 1972, not in an ancient ruin, but inside the nuclear industry. Uranium from Gabon arrived for processing, and one measurement did not look right. Natural uranium has a very steady fingerprint. Almost everywhere on Earth, the amount of uranium-235 sits close to the same tiny fraction. That tiny fraction matters because uranium-235 is the isotope that can keep a fission chain reaction going. If the number is off, something has changed the fuel. The Oklo material was depleted. It had less uranium-235 than expected, as if part of the fuel had already been burned before humans ever built a reactor. That is a much better hook than just saying there was uranium in a rock. The mystery is, what could burn nuclear fuel 2 billion years before nuclear engineering? The answer was not aliens, a lost civilization, or a forgotten power station. It was deep time. 2 billion years ago, natural uranium was different from today. Uranium-235 decays faster than uranium-238. So the further back you go, the richer natural uranium was in the chain reaction isotope. At Oklo, the timing was just right. The uranium was concentrated enough, the isotope mix was stronger than modern natural uranium, and groundwater moved through the ore. Water is the key detail that makes this feel almost engineered. In a reactor, water can slow neutrons down, and slowed neutrons are more likely to trigger more fission. So the rock had fuel, and the groundwater acted like a natural moderator. No control rods, no turbine hall, just chemistry, geology, and physics lining up. But the water also gave the system a break. As the reaction heated the deposit, water could boil away. Without enough water, the reaction weakened. Then the rock cooled, water returned, and the reaction could start again. Oklo may have pulsed through cycles rather than burning steadily like a fire. That is one of the most interesting parts of the story. The same water that helped switch the reactor on also helped switch it off. Oklo was not one glowing cave. Scientists have identified multiple natural reactor zones in the area, each preserving traces of ancient fission inside the ore body. And the evidence is not just missing uranium-235. Fission products and isotope patterns also support the conclusion that nuclear reactions really happened there. The scale is strange too. These were not powering reactors, and they were not explosions. They were natural fission zones running at modest power compared with modern reactors. That modest scale makes the discovery more believable, not less. Oklo worked because it sat inside a narrow physical window where enough conditions were true at the same time. It also explains why this is not happening everywhere today. Modern natural uranium has much less uranium-235, so the ancient isotope window is mostly closed. The aftermath may be even more useful than the reaction itself. Some fission products stayed close to the reactor zones for enormous spans of time. That is why Oklo still matters to nuclear science. It gives researchers a rare natural comparison for how radioactive materials can move, or not move, through rock over deep time. It is not a perfect copy of a modern waste repository, but it is a real experiment that nature ran, buried, and left for humans to discover 2 billion years later. The careful version is important. Oklo was not evidence of ancient technology. It was not a prehistoric power plant. It was not proof of a vanished civilization. The truth is cleaner and stranger. A rock deposit had the right fuel, the right age, the right water, and the right geometry for nuclear physics to happen naturally. So the final verdict is fact. Earth once made its own nuclear reactors at Oklo, and the best part of the story is the isotope clue that gave the secret away.